Students, now we are going to study that what if we drop something, an object from the top of a circular track. Okay, so how far this will remain in circular motion. Okay, so you just look at this. I'm just dropping this. So you see that if you see that in slow motion, so this goes up to this and then this drops down there. Okay. So this is the case when you drop this from rest. So this, like, I'll be proving this mathematically that this would go like if we talk in terms of angles. So if here is the center, like if you take the center of this circular track, so right now if that theta is 0, so when it reaches this and when it is leaving this circular surface, so this has rotated up to an angle of 48.2 degrees. So I'll be proving that mathematically now. Okay, let's prove that mathematically, that how come the particle can rotate up to a maximum 48.2 degrees while remaining in the circular motion. Okay, now suppose this is a semicircular a hemisphere over here, and I have just drawn its cross section, and here is the center of this hemisphere. Okay, let me call this point O, and initially we have here is the initial position from where we're going to drop that particle. Let me call this point A. Okay, so this is the initial velocity here, which is u. Okay, so now this is the level at which we have the potential energy equal to 0 over here. Okay, so now initially we have this is the radius over here, and suppose the mass of the particle is m. So as you know, we always talk about the initial case and then the general case. So initially we have the potential energy as equal to mgr. Okay, and the kinetic energy is going to be half mu square. Now let's consider the general position of our particle. Okay, now suppose here is that general position. This has rotated up to theta degrees, and now it is over here. Okay, I'm going to show the weight like this. This is the mg. Now since the particle is moving on a surface, so we have this is the r over here. Okay, and if you look at this, this is theta, so this is going to be theta as well. Okay, and now I will be resolving this mg so that I can determine the value of r. Okay, so this is going to be, let me use this black marker, this is going to be mg cos theta, and I don't need this component right now. Okay, so I have resolved the weight over here. Now let me see that what is the generally what are these energies. Okay, so generally we have the potential energy. If you look at this now, this is your radius. Okay, so we have to see that how much is how much is this over here. So this is going to be r cos theta. Okay, so the potential energy is going to be mg r cos theta, and the kinetic energy is half, like here right now this is the velocity over here, so the kinetic energy is going to be half mv square. Now from the conservation of energy, we have this, like the sum of the energies initially equal to the sum of the energies generally. So we have this mg gr plus half mu square, that is equal to the half mv square, and then plus mgr cos theta. So you know that we have that F equal to ma for the moving object, and like this is for the linear acceleration. So when we talk about the circular motion, so this becomes F equal to mv square over r. So from this relation we shall take out the value of mv square over r, and again over here, since this is like as long as this is moving, this is maintaining its circular motion, so this F is going to be mg cos theta minus r, that is equal to mv square over r. Okay, so let me call this relation number 1 here, and this is the relation number 2. So we have to algebraically manipulate these two equations to determine, to have a relationship between this theta and the velocity. Like we want to see that how much this would be rotated when we release this from rest, or what can be the maximum speed through which we can release this object from the point A. Okay, so I will be taking out this mv square over r from here, and I'll be putting that into the first relation. Okay, so by simplifying this equation, second equation, I get the expression for mv square over r. Okay, so I'll be substituting this into this relation over here. So now this would become, let me erase this. Yeah, I can erase this. Okay, now this would become mg cos theta minus r, and I have all this. This is mu square over r minus 2 mg cos theta plus 2 mg. Okay, so I'm just going to get the value of minus r, because basically I'll be putting that r equal to 0, because you see when this object was like, it started from here, it is going up to this. So when it loses the contact with this circular surface, then r will be 0. So we can put r 0 over here. Okay, so this will become, when you put r equal to 0 and you bring this 2 mg cos theta to this side, so this will become 3 mg cos theta, that is equal to mu square over r. I'm sorry for these lights, guys. Okay, they're reflecting in the board. Okay, so please excuse me for that. Okay, so this is plus 2 mg. Okay, so now since we just dropped this from the top of this circular track over here, so you must allow me to put this u 0 in this relation. So when you put this u equal to 0, so all of this is eliminated. So and this mg is cancelled with the mg. So we have this cos theta, that is equal to 2 over 3. And if you find this with the calculator, this angle is going to be 48.2 degrees. Okay, so we have proved this mathematically, that when you drop anything, as I showed you by dropping that marble from the top of that circular tape, that it would be rotated up to a maximum angle of 48.2 degrees. Like if it goes up to this, for example, suppose if this angle is 48.2 degrees, then this will lose contact with this circular surface. Okay, now there is another case where you can like there is a case that what would be the initial velocity if this is simply it loses the contact with this circular part right in the beginning of this motion. So for that purpose, you will have to put theta equal to 0. If you put theta 0 like in this equation without putting u0 over here, so you will have like when you put theta 0, this cos theta becomes 1. Okay, so you have 3 mg and then minus 2 mg, that is equal to mu square over r. So this will give you u square equal to gr, and this u is going to be square root of gr. Okay, so the velocity, if the initial velocity, let me write it over here, if your u is between 0 and under root of gr, then your theta is going to be between 0 and 48.2 degrees. Okay, thank you very much guys. In the next video I'll be coming up with some questions related to this kind of the situation.